In this section, we will look at determining the horizontal shift of a sinusoidal function. Going back to the general form of a sinusoidal function, the final value to explore is the effect of the h value, and the h is within the argument of the function. So we're going to look at a couple of examples and compare some graphs in order to see what the effect of that is. So we're going to compare f of x equals 4 times the cosine of the quantity 2 times x, and g of x equals 4 times the cosine of the quantity 2 times the quantity x minus pi over 4. And we're going to look at what has changed. Now, in order to graph this, I'm going to use Desmos, and the settings that I used, you're welcome to follow along, but I think it's really helpful to know where you can change the settings to make the graph look more like what you want it to. In the upper right-hand corner of Desmos is this wrench, and when you click on that, that's where you can adjust the settings. Now, the only setting that I think is really helpful in you getting a graph that you can make some sense out of is this step on the x-axis. Now, the reason I selected a step of pi over 4 was because I recognized that I had a b value of 2. My b value was 2. And if my b value is 2, then that meant that my period of this function would be 2 pi over that b value. So 2 pi over 2 is pi. And if I break that period or divide that period into 4 equal lengths, well, pi divided by 4 is pi over 4. So that's why I selected a step of pi over 4. So if you want to mimic that, that might help you to follow along with what I'm doing. So I'm just going to erase that, and I'm going to show you when I put in 4 times cosine of the quantity 2 times x, what I got. So here's the graph that I got, and I'm going to take just a second to look at that. Looks like the midline is going through y equals 0, which makes sense to me because there's nothing being added or subtracted on the end. There's no k value. The amplitude does look like it's 4, and the reason I see that is I have a maximum at 4 and a minimum at negative 4. And just like I suggested, the period does look like it's at pi, right? I'm starting at 0, 4, and then I repeat at pi, 4. Here comes the graph of g of x. What happens? So to me, what this looks like is that g of x is simply the graph of f of x shifted to the right. Shifted to the right how much? Shifted to the right. So we started at 0, 4. Now we are at pi over 4, 4. So what has changed? So what has changed is that the graph of g of x is f of x shifted right pi over 4 units. And pi over 4 should feel like it makes sense, I think. And the reason why I think that is because on the inside of these parentheses, we see a pi over 4, don't we? We see a pi over 4. And you may remember from previous classes when you talk about transformations that when you have something like a minus pi over 4 on the inside of a function, on the inside of that argument, it does do a shift in maybe the opposite direction that you expected. You know, you see a minus pi over 4, you might think it's going to shift to the left, but it actually does shift to the right. It's the opposite of that minus. Now I want to point something out to you. If g of x had been rewritten where this 2 that was on the outside of the argument, if that had been multiplied through, then you would have seen g of x equals 4 times the cosine of the quantity 2x minus pi over 2. And now you don't see that pi over 4 anymore. So the horizontal shift can't be identified directly. Of course, you could factor it if you wanted to, but if you want to identify it directly, then you always want to write that argument in factored form. And we're going to take a look at some more examples of that. All right, so in y equals a times the sine or cosine of the quantity b times the quantity x minus h, all plus k, the horizontal shift is represented by the variable h. The horizontal shift shifts the graph to the right, if h is positive. So here's h, and it shifts the graph to the left if h is negative. Now that might feel like the opposite of what I just said, but you need to go back to the way this is written. And if I already have a minus symbol there, which is what this formula says, then this h value really is a positive if it is the way it is. If the h value were negative, then you'd have minus a negative value, which would be a positive. And I'll show you more of that here in just a minute. So let's look at an example. Part A. Identify the horizontal shift of f of x equals the sine of the quantity 2x minus 2 pi over 3. So in order to do that, I need to factor the 2 out. So I'm going to pull the 2 out, and what am I left with? Well, whenever you factor, let's just think of an easier example. What if I said to you, factor 3x plus 6? I bet a lot of you would just say, oh, this is so easy. I'm just going to pull a 3 out and I'm left with x plus 2, right? And you can always check it by multiplying back through. Well, how did you know that was a 2? Well, what your brain actually did was it factored the 3 out, and then it took the 6 that we started with and it divided it by the 3 that we just pulled out. So using that same idea, I'm going to take 2 pi over 3, right, that we're starting with, and I'm going to divide it by 2. Now, we're just looking for a systematic approach here. If you have an easier way, you can definitely use that easier way. But a lot of times people have a hard time factoring a number out of a fraction, not to mention a fraction with pi in it. So what is 2 pi over 3 divided by 2? Well, it's the same thing that 2 pi over 3 times 1/2 is, which is simply pi over 3. So this would become the sine of 2 times the quantity x minus pi over 3. And of course, I can always double check it, because if I multiply that 2 back through, 2 times x is 2x. 2 times pi over 3 is 2 pi over 3. And now in factored form, we can say that there is a horizontal shift of pi over 3 units to the right. Okay, let's try the next one. G of x equals the cosine of the quantity pi times x plus pi over 2, all plus 3. Okay, so I'm going to take the cosine, I'm going to factor out the pi, and if I take the pi over 2 that's in there and I divide it by pi, what do I get? What do I get? I'm going to get the cosine of pi times x plus, let's see, what is pi over 2? Not divided by pi, but let's call it 1 over pi. That's going to get me 1/2, isn't it? So I'm going to have a plus 1/2 on the inside of these parentheses, plus 3. So in this case, my horizontal shift is 1/2 to the left. So when I see a plus 1/2, I'm going to go to the left. When I see a minus pi over 3, I'm going to go to the right. And if you're a little confused about the left and the right and the minus and the plus, again, in the form where we have a minus on the inside of this argument, then we've already taken into consideration doing the opposite. That's what allows us to go to the right. If we have plus, that's the same thing as having minus a negative. And now my h value is negative, and that's what's making it go to the left. I don't know if that helps, but that's the justification for moving right and moving left. In the previous examples, we factored the argument of each sinusoidal function in order to identify the horizontal shift. But what if we hadn't factored? What would that then tell us? So for example, in this example, f of x equals the sine of the quantity 2x minus 2 pi over 3 that factored to the sine of the quantity 2 times the quantity x minus pi over 3, we saw that pi over 3 is the horizontal shift. In the unfactored form, 2 pi over 3 is called the phase shift, since it can be used to determine what we say is how far out of phase a sinusoidal function is in comparison with y equals the sine of x or y equals the cosine of x. In this class, we will focus on the horizontal shift, but to give you a little bit more of a feel of it, to determine how far out of phase a sinusoidal function is, we can determine the ratio of the phase shift and 2 pi. Now, we use 2 pi because it is the period of our parent functions, sine of x and cosine of x. Since 2 pi over 3 is the phase shift for this function, we say that the graph of this function is out of phase, the 2 pi over 3 that we saw was the phase shift, divided by 2 pi, which is the period of our standard sine or cosine function. Now, when we divide that, we get 1/3. So we say that it's 1/3 of a period. Since this number is positive, it represents a horizontal shift to the right 1/3 of a period. What was the period of this function? The period of this function was pi. So 1/3 of a period is 1/3 pi, which is pi over 3, and sure enough is our horizontal shift. Now, again, that may feel a little bit confusing. You may have to listen to that a couple of times. In this class, we will focus on the horizontal shift. For more information on phase shift, there's a supplement that you can have access to that might help. I've put the address on here, and there's also a link in your syllabus. So now going back to the steps involved to sketch the graph of a sinusoidal function, we can now add in the step to show the horizontal shift. So these steps are identical to what we've seen before. We identified the amplitude and whether or not it was a horizontal reflection. We identified the midline. We identified the period and whether or not there's a vertical reflection. Now, new step 4 is to identify the horizontal shift. Still, we're going to divide the period into 4 equal lengths. We're going to, on a graph, make a tick mark on the horizontal axis for each of those 4 equal lengths. And those 4 equal lengths should equal 1 period of the function. On the graph, we're going to determine the location of the midline, which is a horizontal line. From the midline, we will go ahead and mark in the amplitudes, which identify the local maximum and minimum of the function. We'll determine the parent function and what the graph is going to look like. And then we will apply the horizontal shift and sketch one period of the function. So let's look at an example. So let's look at the example where we graph f of x equals the sine of the quantity 2x minus 2 pi over 3. Now, the how-to steps that were listed previously can be used in the order given, or they can be mixed up and used in a way that makes sense to you. On graphs of functions where I can identify that there will be a horizontal shift, sometimes I like to start with that. So I'm going to rewrite f of x as the sine of, and I'll factor a 2 out, and when I factor 2 out of 2 pi over 3, I'm left with just pi over 3. Okay, now I'm still going to write down things like what's the amplitude, and that amplitude is the absolute value of the number in front of the function, so that's going to be 1. The midline in this case, there is no number being added or subtracted on the end, so that's going to be y equals 0. The period is going to equal 2 pi over my b value, and my b value is 2, so 2 pi over 2 gives me pi. And I'm going to take that period of pi and I'm going to cut it into fourths. So that means that each tick mark will be pi over 4 units. And that's along my horizontal axis. So starting at the origin to the right, I have pi over 4, 2 pi over 4, which is pi over 2, 3 pi over 4, and 4 pi over 4, which is pi. And I could do that to the left as well. I think for now I'll just start by marking it on the right. And then of course I'm going to mark my vertical axis. So I've got my amplitude at 1 and my midline at y equals 0. So from that midline of y equals 0, I'm going to go up 1 and I'm going to go down 1. Okay, so I know that I'm not going to see anything larger than a y or an output of 1 and nothing smaller than -1. Now, here's the next thing that I like to do. I like to start out by graphing what would this function look like if there were no horizontal shift. So in other words, what if it was just f of x equals the sine of 2x? What if, so in other words, I'm comparing it to a parent function, right? So let's just say I had g of x equals the sine of 2x. So we would still have the same amplitude, we'd still have the same midline, we'd still have the same period. And the way that that would look, because it's a sine function, is I would be starting at the midline and I'd be ending at the midline, and then halfway between I'd be at the midline. At pi over 4 it would be going up, and then it would come down, and then it would end at the end of that period, right? Okay, so that is the function without the shift. Now, if I have the horizontal shift in there, and I guess I didn't write that down. Let me write that down. This is going to be a horizontal shift of pi over 3 units to the right. Okay, so now all I'm going to do is I'm going to take that g of x function, which was the sine of the quantity 2x. It did not have the horizontal shift, and I'm just going to move it to the right pi over 3 units. So the point that started out at the origin, 0, 0, that point now moves to the right pi over 3 units. Now, in some cases, you have to estimate where that's going to be. So I know that pi over 3 is larger than pi over 4. So I'm going to estimate it's about right there. And then this point, my maximum is going to be also to the right. Put a point there. At pi over 2, I'm going to move to the right. Pi over 3. And you can start to see it forming. At 3 pi over 4, I'm going to move to the right. and finally pi is going to move to the right. So I end up with this graph. That graph in red is a graph of f of x, which represents the graph of g of x that had no shift. F of x now is a shift of pi over 3 units to the right. In this example, we're being asked to graph g of x equals the cosine of the quantity pi times x plus pi over 2 all plus 3. So to begin, the first thing I'm going to do is I'm going to rewrite g of x in factored form so that I can clearly see what the horizontal shift is. So when I factor pi out of pi over 2, I'm left with 1/2. Okay, so let's identify a few key things here. We have an amplitude of the absolute value of the number on the outside of the cosine, which is 1, and that is positive, so there is no horizontal reflection. The midline, there is a 3 on the end, so that midline is y equals 3. The period is 2 pi over the b value of pi, so the period is 2. And there is a horizontal shift of 1/2 unit to the left. Okay, so I'm going to go about this in a similar way that I've done before, where maybe I'll take a look at the parent function to begin with and then apply the shift. Before I do that though, let's talk about how I should mark off my x-axis. So I'm going to take that period of 2 and I'm going to divide it into fourths. So 2/4 gives me 1/2. So on my x-axis, I have 1/2, I have 2 halves, which is 1, I have 3 halves, and I have 4 halves, which is 2. And because I have that horizontal shift to the left, I'm already thinking about the left-hand side of this axis. So I'm going to go ahead and mark that. -1/2, -1, -3 halves, and -2. Okay, I have a midline at y equals 3, so 1, 2, and 3. And then from there I have an amplitude of 1. So I'm going to go up 1, and I'm going to go down 1. So I'm going to have nothing higher than 4 and nothing lower than 2. Now, this is a cosine function. So if I were to look at, say, a parent function, I'll call it h of x, where there is no shift. So maybe it would just be the cosine of pi x plus 3. We want to think about what might that look like. So we would start at 0, and we know that a cosine function starts out at its highest value. So for this situation, that would be at 4. And then that would be the highest. And then I would see that value at the end of the period at 2. Halfway between, I would be at my lowest. And then, of course, 1/2. My graph is a little funky there. I would be at the midline. Okay, so something like this. That's what the function would look like without the shift. Now, if I apply the shift, it is exactly the same picture, only now, I'll put this one in black, only now it's been shifted to the left 1/2 of a unit. So the point that was at 0, 4 now shifts to the left and is at -1/2, 4. The value at 1/2, 3 moves to the y-axis, and each one of these is basically just moving 1/2 of a unit to the left. And so I'm going to get a picture that looks like this. So the graph in black is my g of x function that represents that horizontal shift of 1/2 unit to the left. Another thing to keep in mind is if you ever want to double check your work, you could always make a table of values. And for example, you could put in 1/2. If I put in 1/2, let's just say what is g of 1/2? G of 1/2 is the cosine of pi times 1/2 plus 1/2, 1/2 plus 1/2 plus 3. Well, 1/2 plus 1/2 is 1, and that is 1 times pi. The cosine of pi is -1, and -1 plus 3 is 2. So I would expect, I'm just sort of making a mess here, I would expect that at an input of 1/2, that this function with the horizontal shift should have an output of 2, and sure enough, it does. And I could do that for all of the different values that are on this function. Now let's try graphing h of x equals 2 times the sine of the quantity 4x plus 5 all plus 1. I'm going to rewrite h of x as 2 times the sine of the quantity. I'm going to factor out that 4, and when I do that, I'm left with, on the inside, pi over 4 as my horizontal shift. Let's go ahead and just write that down. Horizontal shift is going to be pi over 4 units to the left. I have an amplitude of the absolute value of 2, which is 2, and no horizontal reflection because there's no negative on the front of that. The midline is the line y equals 1. The period is 2 pi over my b value of 4, which is pi over 2. And I'm going to take that period and I'm going to cut it into fourths. Again, we're cutting it into fourths to mimic the behavior of the unit circle. So pi over 2 divided by 4 is the same thing as pi over 2 times 1/4, which is pi over 8. So on my xy axis, I'm going to mark off pi over 8, 2 pi over 8, which is pi over 4, 3 pi over 8, and 4 pi over 8, which is pi over 2. And because I'm noticing a shift to the left, I think I will go ahead and mark the left-hand side off as well. So I'll just mimic those values on the left. Okay, there we go. I have an amplitude of 2 and a midline of y equals 1. So I'll mark 1 up here for the midline, and then I'll go 2 units up. That's going to be the top of my graph, and then 2 units down. So -1, that'll be my lowest value. Okay, now this is a sine function. So if I were to think of the function without the shift, so 2 times the sine of 4x plus 1, what does a sine function look like? This sine function would be at 0, it would be starting at the midline, and my midline is at y equals 1, so I would have a point at 0, 1. I would see that point repeating at the end of the period, so pi over 2, 1, and I'd also see it halfway through. At pi over 8, which is halfway between 0 and pi over 4, I would be up at the top point at 3, and then at 3 pi over 8, -1, I would be at the lowest. So without a shift, this is what that function would look like. We're calling this f of x. Now, all I have to do to get h of x is to take that picture and shift it to the left pi over 4. So shifting to the left pi over 4 is me shifting 2 tick marks to the left. So I have a point at -pi over 4, 1. I have a point at negative pi over 8, comma 3. I have a point at 0, comma 1. Let's go ahead and start to sketch this out so I don't get lost in it. I have a point at pi over 8, comma negative 1. And my last point is going to be pi over 4, comma 0. So this function in black is the function I was asked to graph, which is a shift to the left of pi over 4. So let's try one more that we're graphing, and this one has a lot going on. It says to graph f of x equals negative 2 times the cosine of the quantity 2x minus pi over 2 all plus 1. So I'm first going to rewrite f of x as negative 2 times the cosine of the quantity. I'm going to factor that 2 out. And when I factor a 2 out of pi over 2, I'm left with pi over 4. All right, and now I'll just start the process of identifying things. So what is the amplitude? The amplitude is the absolute value of the number in front of the function. Absolute value of negative 2 is 2. And I'm going to make a note to myself that because I have a negative on the outside, I can expect there to be a horizontal reflection. I also see that I forgot to write what the horizontal shift is. So let me go back up here and say that the horizontal shift is going to be pi over 4 units to the right. Okay, midline is that number on the outside, so that's going to be y equals 1. The period is equal to 2 pi over my b value. My b value is 2, so that's period of pi. And now I'm going to take that pi and I'm going to divide it into fourths. So each one of my tick marks is going to be pi over 4. So pi over 4, 2 pi over 4, which is pi over 2, 3 pi over 4, 4 pi over 4, which is pi. And in this situation, I am shifting to the right, so I can mark the increments on the left, but it's not as crucial this time because I know I'm not moving over to that side, but I'm going to go ahead and do it anyway. Okay, midline is at y equals 1, and I have an amplitude of 2, so I'm going to go up 2, and I'm going to go down 2. Okay, so now what I want to do is to graph this, I want to take a look at the parent function. So let's just say g of x is equal to negative 2 times the cosine of 2x plus 1. What would this graph look like? So we know that a typical cosine function at 0 starts at its highest value. Because we have that horizontal reflection, however, instead of at 0 starting at our highest value, we'll be starting at the lowest value, which is at 0, negative 1. That is going to repeat at the end of the period, which is at pi. Halfway in between there, at pi over 2, I'm going to hit the maximum. And at pi over 4 and at 3 pi over 4, I'll be at the midline. So if I connect these points, I get the picture of the graph without the horizontal shift. Now to apply the horizontal shift, all that I have to do is take this graph in red and shift it to the right pi over 4 units. So I'm going to shift 0, negative 1 to pi over 4, negative 1. I'm going to shift pi over 4, 1 to pi over 2, 1. That maximum value at pi over 2, 3 moves to 3 pi over 4, 3. And you can sort of start to see this shift. And if I just continue down the line, you'll see that it is an identical picture, just shifted to the right. So that's what the graph of -2 times the cosine of the quantity 2x minus pi over 2 all plus 1 looks like. In this example, we're being asked to write a sinusoidal function based off of a given graph. We're being asked to find not only a sine function, but also a cosine function. So one of the functions will have to have a horizontal shift. So we'll begin by just identifying a few features of this graph. I can see that the highest that this graph gets is a y value of 2, and then it doesn't get any lower than -6. All right, so the midline is the value that is in between those two. So maybe we can just count, or maybe you'll remember that I said that the midline is equal to the highest value plus the lowest value divided by 2. So that gets me, let's see, 2 plus -6 is -4, divided by 2 is -2. So the midline is going through y equals -2, which it does look like that. The amplitude is the distance from that midline to the highest and the lowest values. So it looks like I'm going to have an amplitude of 4, amplitude of 4. And the period, what is the period of this function? It looks like I'm starting at 0, -6, and I don't see that value again until I see pi. So the period is pi. Of course, that's not my b value, that's just the period. Okay, so let's start with the function that doesn't have a shift. Does this graph look more like a parent sine function or a cosine function? Think about that for a second. In my opinion, this looks like a cosine function that has been horizontally reflected. And the reason for saying that is that I know that a cosine function at 0 is at its highest value and a sine function is at its midline. This one's not at either of those, but it is at its lowest value. So I think that this looks like a reflected cosine function. So I'm going to say that this function is, I'll call it f of x, is equal to, I'm going to put that amplitude on there, but I'm going to put a negative in front of it, -4 times the cosine of, now what is my b value? If my period is pi, then remember the period is equal to 2 pi over b. So if I solve that equation for b, multiply both sides by b, divide by pi, I get a b value of 2. So I'm going to say -4 times the cosine of 2x, and then I'm going to hook on that midline, which is -2. So I can write plus -2, or I can write -2. Now, there are other ways that I could have written that. If I did not want to put a negative in front of that 4, I could have just written that as a +4, but if I did that, then I would have had to have a shift. I would have said 2, and then in parentheses, x, and maybe I'm thinking to myself, well, it looks like it was a normal cosine curve, but shifted to the, like this is a normal cosine curve, right? Up at 0, 2, shifted to the right, pi over 2 units. So shifting it to the right pi over 2 units would be minus pi over 2, and still -2. Infinite ways that we could write this. If I wanted to write this as a sine function, a normal sine function, remember, hits at 0 hits at its midline. I would have to shift this one to the right pi over 4 in order for that to happen. So another way to write this would be 4 times the sine of 2 parenthesis x minus pi over 4 minus 2. There are lots of different ways. Be creative, try to think of some others, and then of course you can always check Desmos to see if you've got them correct or not. Now let's look at a word problem. Outside temperature in a U.S. city over the course of a day can be modeled by the sinusoidal function d of t equals 50 minus 7 times the sine of the quantity pi over 12t, where t is the number of hours since midnight and d of t is the corresponding temperature in degrees Fahrenheit. Graph this function over one day, describe the practical significance of the period and the amplitude, and then answer the question, what time of day will experience the highest and the lowest outside temperature? So I think if we graph this to begin with, a lot of these other questions will fall into place. Before we graph it, however, I want to make sure that we are clear on what the variables are and what they represent. So t, which is the input, represents the number of hours since midnight, and d of t, which is the output, is the corresponding temperature in degrees Fahrenheit. Okay, so I'm going to identify the amplitude, same process as before. The number that is connected to the front of that sine function is a -7, so that means it has an amplitude of 7. The negative tells me that there is a horizontal reflection that I need to pay attention to. There is a midline. The midline is the number that's added or subtracted on the end. In this case, there's a 50. Even though it's not at the end, I could rearrange it so that it is. So y equals 50 is my midline. The period is equal to 2 pi divided by that b value of pi over 12. And 2 pi divided by pi over 12 is the same thing as 2 pi times 12 over pi, which I believe is 24. Okay, so, and there's no horizontal shift. So I'm going to go ahead and label these axes. My horizontal axis is hours since midnight. And my vertical axis is the temperature in degrees Fahrenheit. Okay, so my period of 24, I'm going to divide that by 4, 24 divided by 4, because I need to figure out how to break up my horizontal axis. I'm going to make each one of these tick marks equal to 6. Now I probably could spread this out a little bit, but I'm going to just stay with what I've been doing. All right, so 6, 12, 18, 24. I have a midline at 50. So I'm going to have to space these out. I think I'll make each one of these tick marks on the vertical axis be 10, and those represent degrees. So 10, 20, 30, 40, 50, and 60. So it's not going to be exact, but it'll be good enough. Okay, so my midline is at y equals 50, and then my amplitude is going to be 7 up and 7 below that. Now, this is a sine function, and I know that a normal sine function would start at 0 and would have a point at the midline. Okay, so I'm going to go ahead and mark that in. So 0 and at 50. And then that's going to repeat at the end of the period, and it's going to repeat midway through the period. Now, normally what happens is from that first initial point, my curve goes up. But in this case, because of the horizontal reflection, it's actually going to go down. So from 50, if I go down 7, I'm at about 43. I'm actually at 43. And so I'm going to put a point there, and it's going to come up. And then at 18, I will be at 57. So that represents one period of this function, okay? Now, describe the practical significance of the period and the amplitude. What do you think? What do you think this 24 represents? Well, because we labeled the horizontal axis as hours, I'm going to say that the practical significance of the period is that every 24 hours, this temperature repeats. So 24 hours, the temperature repeats. I'll write this out. Every 24 hours, the temperature repeats. Okay, and then what about the amplitude? So the amplitude is 7, and so what I would say, an amplitude, by the way, 7 is a vertical change, and we know that our vertical is degrees Fahrenheit. So I would say that there's a variance each day in temperature. Variance in temperature each day of plus or minus 7 degrees Fahrenheit. And that's, of course, from the 50 degrees, which is my midline. Next question, what time of day will experience the highest and the lowest outside temperature? What time of day? So the highest seems to be at 57 degrees Fahrenheit, and that's happening 18 hours. So let me just write this out. 18 hours after midnight. What time is that? So that would be 6 p.m. The lowest temperature is at 6. At 6. So that would be 6 hours after midnight. Or 6 a.m. And I think we've got it from there. So a couple things to point out. It's just so important to make sure that you know what your variables represent, and then to mark them on the axes. The practical significance of the period, because the period is along this horizontal axis, is going to be labeled with however you labeled your horizontal axis. The amplitude, because that has something to do with the vertical axes, that's going to be labeled with however you labeled your vertical axis. So super important. Here's an example where we are not given a graph, we are not given the equation of the function. It's our job to determine the equation of the function that best models this. So we have a Ferris wheel at the Puyallup Fair in Washington State. It has a diameter of about 70 feet, and it takes 3 full minutes to complete the rotation. Passengers board from a platform 10 feet above the ground. Write an equation for a rider's height above the ground. I'm going to underline this. For the rider's height above the ground as a function of time in minutes. Okay? Now, that sounds like a lot. So sometimes if I'm able, I might draw myself a picture. So I know what Ferris wheels look like, right? They look like circles. There it is. There's my Ferris wheel. And it has a diameter of 70. So from the center, all the way across is 70, all the way down is 70. So that's going to be, that height, let me just put it out here, is going to be 70, right? 70, was it feet? 70 feet. Doesn't want to keep that 70 on there. Okay, but the passengers board from a platform that's 10 feet above the ground. Okay, so that platform is 10. So 10, 70, and then another 10. Okay. And it takes 3 full minutes to complete the rotation. So they want me to graph this on an XY axis. So let me I'm going to do a rough sketch of this because sometimes that's what you have to do. And I'm going to label the horizontal axis as, what am I going to label that as? Time in minutes. So time in minutes. And the vertical axis is going to be the height above the ground. The height above the ground. And that is in feet. Okay, so when the writer first gets on at time 0, right, they're sitting right there. They are 10 feet above the ground already. Okay, they are 10 feet above the ground already. And what we know is that it takes 3 minutes to complete a full revolution. So at the end of 3 minutes, my writer, or me, is back at that platform. Okay? Now that's the lowest I'm going to be. So if I think about this, that's the lowest this graph is going to be. If that's the lowest this graph is going to be, does that represent a sine function or a cosine function? Well, it could be either, but if I'm not going to do a shift, then this would be an example of a reflected cosine function, because it's not going through a midline like a sine function would. It's not going through the maximum like a positive cosine function would. It's hitting the lowest value, which is a reflected cosine function. So if this is a cosine function and I'm hitting my lowest value at 0 and 3 minutes, then I must be hitting my highest value halfway between, which would be after 1.5 minutes. 1.5. And that's going to be up. Where's that going to be? Let's see here. So if this is 10, if this part here is 10, and this part here is 70, then I am sitting, it looks like, at 80 when I'm at my tallest. So let's see, can I get that on here? 10, 20, 30, 40, 50, 60, 70. And it looks like I ended that a little too soon, so I'm going to erase this and go a little bit taller. How about that? So 10, 20, 30, 40, 50, 60, 70, there's 80. And this is the height above the ground. Okay, so at 1.5, I'm at 80, and that's my highest. Halfway between there is going to be about right there and about right there. And at those points, I'm going to be at my midline. What is my midline? The midline is, remember, the midline is, let me write this out. The midline we can write as the equation y equals, we're going to take the highest value, we're going to add that to the lowest value, and we're going to divide by 2. So 80 plus 10 is 90, 90 divided by 2 is 45. So at 45, I'm going to be at the midline, and I'm also going to be the midline here. So here's how this graph looks. Now, why did I draw the graph? Because they didn't ask me to. Well, I drew the graph because I feel like now, looking at this picture, I can write an equation that represents this function. I'm going to call this function, how about we call it f of x, and I'm going to start out with the amplitude, which, what did I say that the amplitude was? I don't think I said what the amplitude was. If the midline is 45, 45 to 80, and 45 to 10, I think is 35. Does that sound right? Amplitude is 35. And I'm going to remember that I want to put a negative on the outside of that to show the reflection. I said it looked like a cosine function. And let's see, what's my b value? Well, my period is 3 minutes, and I can set that equal to 2 pi over b and solve for b. Multiply both sides by b, divide by 3, I'm going to get 2 pi over 3x. And then the only thing left to put on there is plus the midline, which I said was 45. And that is the function that would model my rider's height above the ground as a function of time in minutes. And I would encourage you to try a couple of different choices for the minutes. You know, what is f of 1.5? What is that? Go ahead and substitute it in. And I hope that when you do that, you come up with 80 feet above the ground.